I'm Richard Overstreet again, and I'm a postdoc at P&L, and this is our work on graphical neural nets for mass spec MS prediction. So starting out with a motivation for this work of why you might want to use deep learning, take a look at a tool called QCXMS, which is very good at computing mass spectra from first principles, where you give it a molecule, you run some conformational sampling, you explicitly model the fragmentation, and then from this explicit fragmentation modeling, you get out a resultant spectra. Now, the one drawback to this particular approach is that it takes a considerable amount of time to actually get to the end result of a spectra. So for capsaicin, for example, at 40 electron volts, this one prediction took approximately 24 hours to complete across 12 compute nodes. So if you need to do high throughput screening where you need to get a prediction now, not a day from now or a week from now, this is not exactly the best approach. So that leads us to different approaches for applications of deep learning to MS prediction. So we generally have two approaches in the literature: fingerprint-based approaches and GNN-based approaches, which we'll get to in a second. So for fingerprint-based approaches, you generally take the molecule, you pick an off-the-shelf fingerprint, plug that into your neural net black box, and then you get out a spectral prediction. Now, where the power and the benefit of GNNs come from is you can explicitly represent the molecule as input into your neural net black box. So there's no assumption step here of choosing a fingerprint that might be relevant to fragmentation or to classification of fragmentation pathways. So this is a much more powerful technique that's actually borne out in the literature with test set scores of 0.15 versus the NIMS fingerprint architecture of 1.57. So the GNN wins out over fingerprint-based approaches. Now, given the inherent performance benefit the GNNs provide for the task of MS prediction, we wanted to ask a fairly fundamental but potentially very powerful question: is, can we add information to the graphical representation of our molecules that might aid in the embedding of the molecular embedding for MS prediction? So we came up with three models for investigation. Our control model was graphical representations with no edge features between atoms I and J. An RdKit representation, which is just a categorical edge feature representation corresponding to bond orders, so single, double, triple bonds, aromatic bonds, things of that nature. We then switched to more complicated representations. With XTP, we were able to derive Weiberg bond orders and harmonic force constants from quantum chemistry. And then finally, we wanted to take a look at the effects that bond association energies played on the MS prediction quality. We used an alphabet neural network developed at NREL to calculate the acyclic bond association energies for each of the bonds on the graph, and then plug that into our neural network. So for dataset aggregation, we were using NIS20 and a variety of different databases to ultimately aggregate three different data sets: one for RdKit, XTP, Alphabet, into structural databases for our different graphical representations. Our neural net was comprised of 10 layers of graph attention V2 convolution, 8 heads apiece, going into global mean pooling with a linear output layer. For our training regime, we wanted to get aggregated statistics about the GNN performance, so we performed 5 random allocations of our data set into both training and test. We carried those allocations forward to each of the different models to preserve the performance metrics across the different models. For our data set, we're training on roughly 30,000 spectra, 30 to 45 electron volts with the M+H+ precursor type, across 2 different instruments, the Agilent QTOF and the Thermo Orbitrap. We explicitly made a design choice to exclude peptides from our data set, since we didn't want to reinvent the wheel of peptide embedding or peptide MS prediction, since there's already some great neural nets out there that already perform peptide MS predictions fairly well. We also restricted our molecular weight range to less than or equal to 500 grams per mole. So taking a look at the test set cosine similarity score, we can start to see a hierarchy of model performance. We have our control model on the bottom. Then we have the RdKit model as the next best performer. That's the next most complicated model. Then we have XTP, and finally we have the alphabet bond association energy model as the top performer here. So aside from average metrics, we can start to pull apart the test sets and see exactly where the benefits for our edge features are making a difference here. So for each given prediction, we can aggregate the GNN prediction and the versus the empirical the empirical measurement into a cosine similarity score, and we can compare each of the cosine scores between the control model and our model of interest to see exactly where the performance boost is. So for the RdKit model, which again is the categorical representation of edge features, where you could just essentially draw the molecule on paper. Most chemists do that. Where you get single, double, triple aromatic representations of bond order. This model shows a distribution about the diagonal. So there doesn't appear to be a significant boost in performance. There's no global trend where the spectra or the predictions are drastically improved. There's no real shift at the top here or at the bottom, but we do start to see a trend if we actually count the number of predictions above and below the diagonal. We can aggregate that into a metric for performance, and that score for just simply adding categorical edge features is 1.27. So we are seeing a slight boost in performance, which corresponds to the cosine similarity score average metrics. One trend that I wanted to point your attention to here at the bottom of the slide is that we have some chemistries that tend to not perform well. These are at the very absolute bottom of this figure here. That's the location they would correspond to. So these are things like aromatic halogens, aromatic nitrogens, oxygens, and rings, things of that nature that generally tend not to perform well in the neural net. So keep an eye on this part of the slide if you want to see what tends to not work well. And we'll take a look at some actual predictions up here for the best performing model. So the next model is the XTP model. It seems to show a slight increase in performance relative to the RdKit model and relative to the control model. So we have a model performance score of 1.3. But looking closely at the control model versus the XTP model in terms of cosine score versus cosine score, what we can see is we get a net boost with molecules that tend to perform well in the control model. So that's a little bit interesting. There's no net shift here at the lower parts of the spectra, and we also start to see that we see the common suspects of aromatic halogens and the like at the bottom part of the figure here. So there seems to be some common core chemistries that aren't very well predicted under this model approach. Now, moving on to our next most our most complex model, where we're predicting bond association enthalpies, or our top performing model here. We have a model performance score of 1.46, where again we see, similar to the XTP model, an aggregation of scores up towards the top, where we have well-performing molecules, and those molecules perform even better when we start to specify bond association energies in the edge representation for a neural net. And again, we still have the same common suspects here: aromatic nitrogens, oxygens, and rings that tend to break the neural net. Now that we've kind of explored the impact that edge features have on graphical neural nets, we wanted to ask a potentially harder question: is what exactly is the GNN doing for its embedding? So we started to play some tricks with the GNN weights. We selected the signals that were relevant to a particular peak in the predicted spectra, plugged that into the weights of our GNN, and we're able to color code or generate scores for each of the vertices, which is an association, or we're taking it as an association between the subgraphical division, or the categorical measure of each of these different molecules. So this is how the GNN is essentially splitting up the molecule for a particular peak. So taking a look in detail at the 2-deoxyadenosine 5-monophosphate molecule here, we can start to see a clear categorical shift in the color mapping of each of these signals, where the yellow seems to associate with the aromatic ring, and then there seems to be a division around the ribose group. So there appears to be some, at least if not chemically meaningful, division with well-separated peaks here. There appears to be at least some natural subgraph division. It's not just randomly picking vertices in the graph to associate with a particular peak. Now, as we move forward here, we'll get into greater levels of ambiguity moving forward. It's kind of hard to directly associate the verdicts classification when the spectra gets more and more complicated. But looking at another case, here we can see that we, using this small dipeptide, we wanted to explore systems that were underrepresented or intentionally underrepresented in the data set. So looking at the system, we appear to see two classifications where we have this particular subgraph and a subgraph involving sulfate. Now, this is a much weaker association here, but it appears to associate with the 56 m/z peak and the 74 m/z peak. So again, the neural net is capable of much more complex representations than we probably are going to get credit for with a simple chemical interpretation of fragmentation. Now, looking at probably the most complex example we'll see today with the prediction of hydrocortisone between the GNN, and this is again the empirical measure. What's apparent here is that the GNN is able to essentially mix subgraph representations for representations of different peaks. So what we expect is happening here is it's just picking and choosing different slices of this molecule and then mixing those up to make a fairly accurate prediction for hydrocortisone. So there's definitely more to unpack here for these different very complex molecules and complex spectra when the spectra is not a simple classification. So finally, I wanted to wrap things up with a case in where things actually start to break apart, going back to those molecules that were the common suspects with the GNN, where it actually starts to break performance. And so looking at 2-chlorophenylaniline, what we can see here is that there is a clear classification for the base peak in the spectra at 125 mass to charge ratio, where the GNN seems to want to actually split apart the molecule or split apart the aromatic ring, which is, I could imagine, would be fairly non-physical for this particular molecule. So it's quite possible that the GNN is relying on prior rules where it's seeing a bunch of hydrogen in place of chlorine, and it's used to that particular substituent, and it doesn't know exactly how to handle this particular graphical representation, so it makes its best guess and slices the molecule along the aromatic ring. So there's definitely more to the story here for chemical perturbations or simple functional group additions like chlorine. So in summary, we demonstrated that edge features can in fact improve the molecular embedding for the task of mass spectral prediction. XTP features appear to be inferior to alphabet features in terms of average test set cosine similarity score and breaking down the test set distribution itself. We're actively looking for different architectures that could potentially improve the molecular embedding. There's some active discussion about how the GNN is incorporating edge features. Right now, we suspect it's being used as a gate rather than being changes being propagated forward. So that's definitely room for improvement. As always, with any deep learning problem, we would like to incorporate larger data sets. And for future work or immediate future work, we would like to combine both the XTP and alphabet models to see if we can get a net performance boost combining those two representations. And we'd also like to dig in further on the interpretability of the GNN, essentially reading the tea leaves of what exactly the representation is encoding. So with that, I'd like to thank our group, especially Ethan King, who's provided many valuable discussions on GNNs and generalizability. Neil Henson, Tom Simone, P&L Research Computing, has given us many thousands of hours of computing resources, as well as the overall mRiverQ initiative that's funding this work. So with that, thank you for your attention and welcome your questions.
Thank you, Richard. We have time for questions. Yes.
Hey, great talk. I just had a quick question regarding, some of those compounds for which the prediction was maybe a little tougher. So knowing that, in fragmentation, sometimes it's, more straightforward bond cleavage. In other cases, especially maybe looking at some of those structures with like the complex aromatic systems, it might involve more, say, rearrangement type of rearrangements that happen during the fragmentation. So have you thought about how you might be able to capture some of that behavior in terms of how you, kind of featureize these compounds?
That's an excellent question. So we've given it some thought. I think we want to focus on edge attributes first to make sure that they're being propagated properly. But that is definitely a concern of having multiple fragmentations or secondary fragmentation pathways. So I can imagine that we could come up with an architecture which would curate the first fragmentation pathway and then update based upon secondary fragmentation pathways for more complex spectra or more complex molecules. But that's something that's would definitely be in active development. Yeah.
Thank you. Yeah, we have time for one more question.
Building off of that, some of what you spoke about with the last case study was that there seemed to be the neural net was making mistakes in what it thought was going on with the aromatic ring. So given that, it seems almost like this is something that could be addressed through a revision of the training set to give more time or experience to the neural net with these aromatic halogens. Is that something that might be possible, or would that cause problems with the neural net recognizing the vast majority of others that it does work well on as of now?
I think that's possible. I think you run into a case of a very small data set sizes when you do that. So with the 2-chlorophenylaniline substituent or chlorides in general, relative to say carbon, hydrogen, and nitrogen, they're very underrepresented in the NIST data set. So you'd have to find a very specialized MS library which addresses those specific molecules and is able to backfill your data set to where you can build trends and then or build a sufficient training set to make a molecular embedding and then combine that with what you already know about existing chemistry. So it's definitely not an easy task to solve per se.